How the world really was before Pangaea. If you type supercontinents into YouTube right now, you'll find dozens of videos talking about Pangaea. Some will mention Rodinia. The bold ones might even bring up Gondwana. But there's a problem with almost everything you've watched on this topic. Most videos start the story at the wrong point. Pangaea existed roughly 335 to 175 million years ago. That's a long time, right? But Earth is 4.5 billion years old. That means Pangaea covers less than 8% of the planet's history. Less than 1/10. The vast majority of Earth's geological history, over 4 billion years, is treated like it never happened. What came before? What landmasses existed when life was still figuring out how to be life? What oceans covered the planet when the only living things were bacteria struggling to survive in a world without oxygen, without ozone, under constant meteorite bombardment? The answer doesn't fit into an easy-to-digest video, because it's unsettling, it's weird, and it'll make you look at the ground beneath your feet in a whole new way. In this video, we'll do what few channels dare. Walk through the complete history of Earth's supercontinents, from beginning to end. We'll start on a planet you wouldn't recognize as Earth. And we'll end at a point that leaves you with a question you'll never stop asking. The Earth that didn't look like Earth. To understand supercontinents, you first need to grasp the early Earth. And it was hell. When our planet formed about 4.54 billion years ago, there were no continents. Just a global ocean of magma. The crust was still solidifying. The sky was a thick mix of water vapor, carbon dioxide, methane, and ammonia, no free oxygen. The sun shone at only 70% of its current intensity. And the moon, the same one you see at night, was much closer. So close that the tides it caused were monstrous, dozens of times bigger than any modern tide. Then, between 4.4 and 4.0 billion years ago, came the late heavy bombardment. Earth was hammered by absurd numbers of meteorites. Any life that might have started earlier was probably wiped out multiple times. But here's the detail most videos skip. Even in that chaos, Earth's crust was already differentiating. Zircon minerals found in Australia, the oldest we know, date back 4.4 billion years. And they suggest liquid water on the surface much earlier than once thought. Not a stable ocean, but water. Pockets of water. And where there's water, something begins. The oceanic crust that formed was different from continental crust. Denser, thinner. Continental crust, the rock type that forms the continents, is less dense and floats on the mantle like foam on soup. That density difference is what made supercontinents possible. But to have a supercontinent, you need continents first. And that takes time. A lot of time. And a process called crustal accretion, bits of crust colliding, merging over billions of years. The first surviving continental cores are called Cratons. Think of them as the planet's bones, the oldest, most stable parts of the crust, 2.5 to 4 billion years old. Some still exist today, buried under modern continents. The Amazon Craton, the rock under much of South America, has parts over 3 billion years old. When you're walking in the Amazon, you're stepping on something older than any animal that's ever lived. Those Cratons were the seeds for the first supercontinents. The forgotten supercontinents. There are at least 6 identified supercontinents before Pangaea. I'll cover each one, and with it show what the world was like back then. Because every supercontinent is also a window into a totally different kind of Earth. Vaalbara, the first world, 3.6 to 2.8 billion years ago. The oldest candidate supercontinent is Vaalbara. The name combines 2 of the world's oldest rocks, the Kopval Craton in South Africa and the Pilbara Craton in Australia. The idea is that these 2 landmasses, now over 6,000 miles apart, were once joined. How do geologists know? Paleomagnetism. When rocks form from magma, magnetic minerals align with Earth's magnetic field, like a compass frozen in time. Analyzing that in rocks from different continents lets scientists reconstruct their past positions. Kopval and Pilbara data suggest they were close, maybe connected 3.6 to 2.8 billion years ago. What was the world like? No free oxygen in the atmosphere. The sky wasn't blue. It was probably orange-red from methane. Oceans had a greenish tint from dissolved iron. No ozone layer, so unfiltered UV radiation hit the surface. And yet, life. The oldest known bacterial fossils, stromatolites, date to this time. Layered structures built by cyanobacterial colonies. You can see their fossils in Pilbara rocks today. They had no nucleus, no mitochondria, just bags of protein and DNA fighting to survive in a world built to kill them. And they made it. Vaalbara probably wasn't one solid mass, more a loose cluster of continental cores. But it was the beginning of everything. You are the continent that never died 3 billion years ago. Next up is UR, and UR has a fascinating detail almost no video mentions. Proposed by geologist Johan Zegers and others, UR formed around 3 billion years ago from Cratons in South Africa, Western India, Western Australia, and possibly Antarctica. What makes UR special? It was never fully destroyed. Pieces survived intact through every supercontinent cycle that followed. Bits of UR were in Pangaea. They went with Gondwana when it broke off. And fragments still exist today in South Africa, India, Australia. UR is Earth's immortal continent, the core that withstood 3 billion years of tectonics. The world during UR was still deeply alien. Plates moved faster than today. The Earth's interior was hotter, mantle convection more intense. Volcanoes were more numerous and violent. And the first eukaryotic cells, with nuclei the kind you're made of, were still over 1 billion years away. Kennerland, the supercontinent of the Great Oxygenation, 2.7 to 2.1 billion years ago. Kennerland is maybe the most important supercontinent you've never heard of. Formed around 2.7 billion years ago, it gathered cores from what's now North America, Greenland, Northern Europe, and possibly Australia. But what makes Kennerland extraordinary isn't its formation. It's what happened during and after its breakup. Around 2.4 billion years ago came one of Earth's most transformative events, the Great Oxygenation. For billions of years, cyanobacteria produced oxygen via photosynthesis. But it got soaked up by dissolved iron in oceans, crustal minerals, methane-rich air. Oxygen just didn't build up. Then the sinks got saturated. Ocean iron oxidized. Atmospheric methane got destroyed. Free oxygen started accumulating for the first time. For most life back then, it was catastrophe. Oxygen is poison to organisms that evolved without it. The Great Oxygenation likely caused the first mass extinction, wiping out entire microbial civilizations that ruled for billions of years. But it paved the way for everything after. No oxygen, no ozone layer. No ozone, no UV protection. No protection, no surface life. The Great Oxygenation set the stage for complex animals, plants, And here's the Kennerland link few discuss. Evidence suggests its breakup, exposing fresh rocks to erosion, helped saturate oxygen sinks and trigger the event. Supercontinents don't just reshape land. They alter planetary chemistry. Nuna, the in-between supercontinent, 1.8 to 1.5 billion years ago. Nuna, also called Columbia, is the best documented supercontinent before Rodinia. Formed around 1.8 billion years ago, it gathered nearly all existing landmasses into one setup. What makes Nuna intriguing is its era, the Middle Proterozoic, which geologists, without irony, call the Boring Billion. And that name says it all. From 1.8 to 0.8 billion years ago, life seemed to crawl. Eukaryotic cells existed, but complex multicellular animals were far off. Evolution was stalled. Why? A recent hypothesis points to Nuna. A massive supercontinent means most land is far from the sea. And it was shallow, nutrient-rich coastal zones, the ocean's cradle, that birthed complex life. A giant continent creates vast, arid inland deserts, biologically dead zones. Plus, evidence shows deep oceans during Nuna had high hydrogen sulfide, toxic to most eukaryotes. Earth was stuck in an evolutionary trap, and Nuna might have been the jailer. Remember the faint young sun paradox, the dim early sun? But Earth didn't freeze thanks to extra CO2 and methane? Nuna lasted long enough to hold that fragile balance. When it started breaking, what followed was brutal. Rodinia, the supercontinent that nearly froze Earth, 1.1 billion to 750 million years ago. Then we reach Rodinia, the supercontinent most videos mention briefly, but it deserves way more. Rodinia formed about 1.1 billion years ago. The name comes from the Russian Rodinia, homeland, motherland. Its layout was wildly different from Pangaea. Rodinia sat at the equator with modern North America at the center, flanked by South America, Africa, Antarctica, Australia, and other fragments still fused. But Rodinia's story is its destruction and the near-apocalyptic aftermath. Around 750 million years ago, it began breaking apart. That kicked off Earth's weirdest climate event, Snowball Earth. Rodinia's rift exposed huge new rock areas to erosion. Fresh rocks suck CO2 from the air via chemical weathering. Greenhouse effect weakened. Earth cooled. Polar ice expanded. And here's the nightmare. Ice is white, reflecting sunlight. More ice, less heat absorbed. More cold, more ice. A runaway feedback loop. Climate models suggest Earth froze solid, from poles to equator. A planet encased in ice, average temps around -50 degrees Fahrenheit. The ocean beneath, maybe liquid at geothermal spots, was life's only refuge. And life survived. Why? Volcanoes never stop. Even frozen, they pumped out CO2. With erosion halted by ice, CO2 built up for millions of years, maybe 300 times today's levels. Extreme greenhouse. Ice melted catastrophically in thousands of years. What came after? The Cambrian explosion, the biggest evolutionary burst in history. First bilateral animals. First eyes. First predators. The biological world we know. Rodinia wasn't just a supercontinent. It triggered the world you live in. Pannotia and the Ediacarans, the transition 600 to 540 million years ago. Between Rodinia and Pangaea, there was at least one more, Pannotia, formed around 600 million years ago from Rodinia's fragments. Pannotia is the most debated. Some geologists doubt it was a unified mass. But its assembly and breakup aligned with a period that's unsettling in a whole different way. The Ediacaran. Ediacaran organisms are the first macroscopic animals in the fossil record, and they don't look like anything today. No mouths, no anuses, no clear nervous systems. Flat discs, fronds, tubes. Some say animals. Others giant fungi. Still others, a separate evolutionary experiment. Multicellular life that arose independently and got erased. Then, around 540 million years ago, they vanished. The Cambrian explosion swept away the Ediacaran world and brought the body plans we recognize, arthropods, mollusks, chordates, ancestors of all life now. Earth was getting familiar, but it wasn't our world yet. The trigger event, the Wilson cycle. But why does this happen? Why do continents keep joining and splitting, like the planet's breathing? The answer lies in a pattern geologists call the Wilson cycle, named after Canadian geophysicist J. Tuzo Wilson, a pioneer of plate tectonics theory. The Wilson cycle describes how oceans open and close over hundreds of millions of years. When a supercontinent breaks apart, new oceans form between the fragments. Those oceans grow, peak, then shrink as dense oceanic crust sinks back into the mantle at subduction zones. Eventually, the fragments collide again, forming a new supercontinent. It's a cycle, roughly every 400 to 600 million years. And here's the part that'll make you see world maps differently forever. We're in the middle of it right now. The Atlantic is opening. The Americas have been drifting from Europe and Africa for 180 million years. But the much older Pacific is shrinking. The Americas are heading toward Asia. Australia too. Sometime in 250 to 300 million years, a new supercontinent will form. Geologists already have names for it. The most famous is Amasia, formed by North America slamming into Asia across the Arctic. Another model, Pangaea Proxima, predicts the Atlantic will stop spreading, a new subduction zone will form along its edges, and continents will converge back into something like Pangaea but flipped. The planet hasn't stopped breathing. It's just in another phase. What happens to life when a new supercontinent forms? We've seen the answer: mass extinctions, radical climate shifts, then a new evolutionary chapter. The next one will inherit a world with humans, or their descendants, or maybe nothing recognizable. We don't know, but the cycle rolls on, witnesses or not. The core conflict, Earth versus itself. There's a pattern linking every supercontinent on this list, and it's unsettling once you spot it. Every supercontinent breakup triggers a chain reaction that reshapes the whole planet. When Kennerland split, exposed rocks altered ocean chemistry. That sparked the Great Oxygenation and wiped out microbial ecosystems that had ruled Earth for billions of years. When Rodinia broke up, intense erosion sucked CO2 from the air. The planet lost its thermal blanket. Earth froze from pole to equator. When Pangaea started cracking, rift volcanism pumped tons of CO2 into the sky. Climates warmed. But that same breakup opened oceans that enabled modern vertebrate diversification. Always the same cycle, destruction that feels final, and that, billions of years later, we see was the foundation for what followed. Every destruction is also creation. Every extinction clears space for something new. But there's a deeper layer that's even more mind-bending. Supercontinents reshape Earth's interior, not just the surface. When a massive continent sits over the mantle for hundreds of millions of years, it acts like insulation, trapping heat that would normally escape through ocean floors. The mantle below superheats. That spawns mantle plumes, hot rock columns rising like bubbles in a lava lamp, uplifting crust from below and helping crack the supercontinent apart. In other words, the supercontinent sets up its own demise. It warms the mantle beneath until the mantle shoves it apart. A self-regulating system of terrifying elegance. Earth isn't passive. It fights back. And every time life thinks it's found stability, the planet rearranges everything. Now think about today. The mantle plumes that will eventually split our continents are already here. One's under East Africa right now, the East African Rift, where the continent's slowly cracking. In tens of millions of years, that rift will birth a new ocean. The Horn of Africa will peel away from the rest. It's too slow to feel, but it's happening, right now, while you watch this video. The time scale that breaks intuition. Before we go on, do this thought experiment. Not because it's poetic, but because without it, the numbers won't stick. Imagine all of Earth's history fits in one day. Midnight is the start, the planet's formation, 4.5 billion years ago. The next midnight is now as you watch this. Life shows up early, around 4 a.m., maybe sooner. But for hours, it's invisible. Just bacteria. Just microbes. The whole day passes. The imaginary sun rises and sets. And still no eyes, no mouths, nothing recognizable. The first complex animals, things with bodies, symmetry, something like a face, arrive around 9 p.m. Dinosaurs at 10:50 p.m. gone by 11:40 p.m. Modern humans? Last 3 seconds before midnight. All civilization from Sumerian cities, Egyptians, Greeks, Rome, Middle Ages, Industrial Revolution, World Wars, Internet today fits in under a tenth of a second. Pangaea? Started at 11:30 p.m. It was nearly midnight when it existed. Vaalbara, the first supercontinent, hits around 5 a.m. while the rest of the world slept. Now scale it to speed. Continents drift 2 to 5 centimeters a year. About the speed your fingernails grow. Ridiculous, right? But that's what moves whole continents thousands of miles over tens of millions of years. India's plate was faster, up to 15 centimeters a year. Crashed into Asia, stacking crust nearly 9 kilometers high. The Himalayas aren't relics. They're still rising. Everest is taller today than when humans first summit. What it all means. Vaalbara, Kennerland, Nuna, Rodinia, Pannotia, Pangaea. 7 setups on a planet that never sits still. 7 different worlds, each with its oceans, skies, chemistry, crises. But I want to end with one idea that haunts me. We're literally made of those worlds. The calcium in your bones settled on ocean floors between Kennerland and Nuna. The iron in your blood came from chemical shifts the Great Oxygenation unleashed. The carbon in every cell has cycled through volcanoes, oceans, forests from unnamed eras. You exist because none of the catastrophes we covered were final. Snowball Earth froze the planet solid, and when ice melted, life exploded into diversity never seen. The Permian extinction killed 96% of marine species, and survivors inherited an empty world, ripe for dinosaurs. The dinosaur extinction handed that world to mammals. To us, every end set up the next beginning. But here's the most uncomfortable part. We're the first species on Earth to grasp this. The first to read a rock and see an ocean from 2 billion years ago. The first to reconstruct worlds no eye ever saw. There's something extraordinary in that. A species born in the last 3 seconds of this 24-hour day, decoding the early morning. And we're the first to tweak the planet's climate on a geological scale in real time. The CO2 we've pumped since the Industrial Revolution isn't the highest Earth's seen. Atmospheres have been far richer. But the speed of change has no geological precedent. Faster than the volcanism that cracked Pangaea. Faster than mass extinction triggers. Earth will survive. It always has. Supercontinents teach a different question. When the planet reorganizes, survivors aren't the old world's dominators. They're the ones who adapt to the new one. The question isn't if Earth survives what we're doing. It's if we survive Earth. Next time you glance at a map, remember, it's a snapshot. A photo from one moment in a story without a memorable start or visible end. Borders shift. Oceans open and close. Mountains rise and erode away. The ground under your feet was once ocean floor. Crossed the equator, was part of nameless worlds. Vaalbara, you are. Kennerland, Nuna, Rodinia, Pannotia, Pangaea. 7 worlds before ours. One more coming. If you made it this far, thanks. You now hold a perspective most folks never chase. Keep it and subscribe.